Hello, welcome to another of our AFRY webinars. My name is Matt Brown. I'm Vice President in the energy part of AFRY Management Consulting. We have a webinar about a very topical subject just at the moment in terms of how to decarbonize shipping and marine transportation. And taking you through the slides today will be Kjetil Ingeberg, who is Director and Head of our Oslo office, and Paola Lualdi, who is a Principal in the Milan office, who've been working on this subject quite extensively. We skip on to the next slide just to say that feel free to ask questions all the way through the webinar using the question panel. We've had some in the registration, and what we will do is, if we don't get through all of the questions in the Q&A, we'll come back to you individually and answer them because we have your details and we can come back to you. And just to say, the slide pack and recording will be emailed to all attendees as soon as they are available. We have 45 minutes today, in case you didn't notice that, and most of these have been 30 minutes, but today 45 minutes. So with that, I will hand it over to Kjetil to take us through the material. Thank you.
Thank you, Matt. Maritime transportation is a backbone of international trade, transport, and logistics. Consists of ships and of ports. At the same time, it's a major source of CO2 emissions and other emissions, which puts us also at the focal point on the ongoing focus on decarbonization of many sectors. So let's start with a short overview of what is actually driving the development in the maritime sector. And decarbonization is not alone. Transportation as such is generally growing. There's a volume growth, especially in container ships. There's a growth in passenger volumes for local and domestic transportation, and there's an increased size and complexity in the fleet, even though we're looking at an asset which has a fairly long lifetime. But there are other issues as well. Decarbonization is the focus today. How can actually we do measures in this sector that contribute to decarbonization of emissions from this sector? As any other sector, it's also exposed to digitalization in economy-wide digitalization and driving new logistics solutions. And not least, very often we see that ports are located close to urban centers, cities, and the interaction with sustainable urban development is often also a very important issue. But let's turn to decarbonization and also look at three main areas. In order to decarbonize a sector, the long-term sustainable platform will always be based on some kind of market development, actually making this sector sustainable in its own regard. We'll look in this presentation into the market development for decarbonization, but also two other very important issues, namely the technology development and also on the policy development. As we're talking about carbon, and carbon is not say goods we can touch or trade or eat or do anything with, is a politically agreed made product that we want to reduce the amount of and get rid of. So the policy development, policy incentives are of crucial importance. Well, let's start with looking into what are we actually talking about. CO2 emissions from shipping makes up around 13% of the EU transportation emissions. That differs obviously a lot among countries. In some countries, the share allocated to shipping, and then including domestic navigation, the international navigation, but also international bunkers, not of all which necessarily is part of the national CO2 registry obligations, can be quite high. Like in countries in the Netherlands and Belgium, with big ports, with a lot of international traffic, they also make up for a lot of the emissions. In general, we're talking about significant source of emissions, especially then in the coastal areas. The other issue is what kind of ships are we talking about? Where will these emissions actually take place? There's a huge difference between different ship types. as I mentioned, container transport is a growing sector, and also container ships we see is worldwide the biggest source of CO2 emissions, along with bulk carriers and oil tankers. We can also note near the bottom, the fourth bottom sector ship type, the cruise ships, has been a lot in focus and actually contributes fairly little to the global CO2 emissions. Nevertheless, we're not only talking CO2, we're talking about other emissions, SO2, NOx, particles, often close to urban areas. So we're not only talking the CO2 emissions, but also the emissions of other local pollutants, where cruise ships, often moored, berthed near a major city, is another issue. So bear in mind, and very much of what we're talking about here is not only CO2, but also other emissions. Also look at the difference between the blue and the red bars at the right-hand side. At sea, the ships will use the main engine, while in port, very often an ancillary engine that is much smaller than the main engine. That means that if we are to reduce emissions from shipping to a significant degree, we need to do something not only with emissions in port, but also at sea. From a study we recently completed for the Norwegian authorities, we find that less than 10% of the emissions from the ship traffic in Norwegian waters actually comes in port. That means we absolutely need to have new technologies that can replace marine gas oil and other fossil fuels while ship is at sea. And that leads us to the technology side. We have some options. The two main options that we have looked into is electricity and hydrogen-based fuels. Hydrogen either in the form of liquid or compressed hydrogen, but it could also be in ammonia, which is a nitrogen-hydrogen chemical compound, which has some, say, attractive characteristics compared to hydrogen. But have a look at what are the technical alternatives. Of course, electricity from grids, when we look at the maturity of the technology and the energy efficiency, is unbeatable. But for obvious reasons, it can only be used in port, what we call shore power or cold ironing. At the extreme, the technical potential would be that shore power can maybe make up for reducing around 10% of emissions from ships. Then there are two other main alternatives, battery electric and hydrogen. Battery electric is fairly mature as a technology given the huge growth in electric vehicles and battery technology. It's still developing. The energy efficiency, the primary energy factor, is also very good. When you put a kilowatt hour from renewable energy into a battery, you will get about 75% of that out in actual propulsion. But batteries are heavy, they have low energy density, and we have a very limited sailing range, which leads us to other alternative fuels. Hydrogen compressed up to maybe 350 bars, or liquefied where it's cooled down to almost absolute zero. Hydrogen is not new. We produce hydrogen for 100 years. Most of hydrogen is produced from natural gas through something called gas reforming. That process will emit CO2 as any other use of natural gas. We could also produce hydrogen from electrolysis. That makes up maybe 2% of the current world industrial hydrogen production. And using a renewable source, that could be a good solution. This is what we call respectively blue hydrogen with gas reforming, and CCS, where we actually capture and store the CO2, and green hydrogen. Problem is that when you go via a primary source all the way to hydrogen back to propulsion and ship, the energy efficiency is quite low, possibly less than 20%. Ammonia has almost the same characteristics, but it's also very poisonous, which also raises some new issues. Then we could also say, well, we have biofuels that's in use and as an alternative in many sectors. We're talking pretty high volumes and energy requirements for shipping. So it's a question about where do we use our limited biofuel resources, and to what extent is it sensible to make them use them in ships instead of in other sectors. Let's look at one example for sailing distances. This chart shows the combination of usable energy per kilogram and usable energy per liter for different fuels. And when I say usable, this is actually then is what is the usable energy for propulsion at sea. MGO, marine gas oil, of the upper left part, is the current solution. It takes little space, it has a high energy volume content per liter, and it weighs relatively little. LNG, and I think that is also a commonly known alternative to MGO, has many of the same characteristics, even though you need some more space on board to carry the same amount of usable energy. Then hydrogen, either in the form of liquid, LH2, or compressed, CH2, or ammonia, requires a lot more space on board. Even though hydrogen is a much lighter fuel, you require much more space on board. While for batteries, they're extremely heavy and they contain very little energy per volume. That means, take an example of today's typical maximum for battery electric propulsion, about 25 nautical miles. Actually, as late as yesterday, it was announced a small ferry in Norway that can go up to 50 miles. But this map shows the most usual ferry routes across the Skagerrak and Kattegat between 3 Nordic countries, and how far could go in battery. And the response here is quite easy. You can't go very far. You need something else, which means we have to find other solutions on the technology side in order to cover a high share of CO2 emissions from ships. So to summarize, in port, direct electricity is an unbeatable solution. While at sea, we have several non-optimal choices, either due to low energy efficiency, low technical maturity, or actually low performance. So we finished last year and early this year, we delivered a report to the Norwegian authorities. We did a wide analysis of how much, what would be the potential for electrification and hydrogen for Norwegian ships or shipping industry in the Norwegian waters. So we analyzed around 4,000 ships, a few 100,000 sailings, 650 ports to find out where is it optimal. And we had some interesting findings. First of all, we need to look into what is the technical potential. Where is it actually possible? As you just see, we cannot sensibly make a ferry go from Oslo to Copenhagen on a battery. It's simply not technically possible. So we analyzed different ship types. The map to the right shows 2 ship types, bulk carriers, the orange lines, and offshore supply ships, the lilac lines, showing the huge difference in how ships actually sail. And that is one important indicator, where can we actually do what? Because an offshore supply ship that goes from a port to a field and back to the same port repeatedly, it's much easier to get a viable business model in place than a ship that goes from A to B to C to D, etc. The other thing we did was to look into the commercial potential. We'll look into the main cost elements. For electrification, we have 4 cost elements. We have the grid capacity outside of the port. We have the shore installations in the port. We have the retrofit on the installations in the ship to use either shore power or battery electric propulsion. And we have the price difference between marine gas oil and electricity. As for the Nordics, that final last difference is quite positive. That is not necessarily the case everywhere in the world. For hydrogen, we looked at the production cost for hydrogen supply then to a ship, both for local electrolysis and for large-scale solutions where you transported liquid hydrogen to the given ports. This showed us a couple of interesting observations. The first one, where in Norway would we actually locate the first installations? The heat map shown now shows where are the cheapest places to get the most possible CO2 reductions in place, broken down to individual ports and ship types. The report, which is publicly available, also shows that there are some ship types that actually are more attractive than others, like ferries and offshore supply ships. The other thing we did was looking into what was the cost development as we introduced the technology into more and more ships and more ports. We made 4 scenarios. The 4 scenarios was a limited electrification scenario where we looked at shore power, we looked at ferries and little else. We had an ambitious electrification scenario. We introduced battery electric propulsion into a lot more different ship types, but with a limited sailing range up to about 25 nautical miles. We had an ambitious hydrogen scenario where we introduced hydrogen using fuel cells on board in a large number of ships. And we had a combination of the ambitious electrification and ambitious hydrogen scenarios. This graph shows how much CO2 emission reduction can we actually achieve. We found that the total emissions in Norwegian waters is in the order of 6 million tons a year. We could have about 20% reduction given these measures if we went to the extremes. But when I say extremes, I really mean extremes. Look at the y-axis. This is the abatement cost in kroner per ton. 1 euro is about 10 kroner. So divide by 10, you have the euro price abatement cost. The horizontal line shows the current EUA price, the carbon cost, the market price for carbon in Europe. As we see, all of these abatement cost curves, they start below 0. That means there are actually places, given the energy and grid costs in the Nordics, that are sustainable and profitable without any kind of investment support or the, say, publicly financed incentives. And we can actually identify which ones they are. But then the abatement cost curves rise quite quickly, up to like 600, up to 1,000 euros, which by any measure would say is far too expensive. That means finding out where to put one's money, where to invest in shore power or in battery electric propulsion or in hydrogen solutions is crucially important to make sustainable value chains. And then the next question is, how can we actually address that question? That is where I'm leaving the word to my colleague, Paola Lualdi in Milan.
Thanks, Kjetil. So if we look at the opportunities of decarbonization of the maritime sector, we can definitely say that the new business opportunities are rising. Some business opportunities can be related to new technologies like hydrogen, or let's say more evaluated and existing technology like cold ironing, electrification of the harbor. And while some of these could be exploited by existing operators, as if we take the case of hydrogen, where till the value chain will be decentralized as it is today, will be similar to the MGO value chain. If we look, for example, at cold ironing, there could be a need for new role, that is a role of an operator that would be a sort of trade union between the port system, the grid, and the ships. Other role could be envisaged in a service provider that could play a role in the electrification of the transport inside and outside the portal area. A key fact to transform these business opportunities into successful business cases is linked to one big challenge, that is the coordination between several players. As you can see from this picture, in the arena of the port and the maritime sector, we have several actors that can go from traditional players like distribution.
It seems as if there's some connections problems from Milan and Paola, so let me jump back in. As Paola started explaining, the value chain for the say decarbonization of maritime consists of quite a few different players. The distribution companies, when we talk electricity, is an obvious player here. The ship owners and the ship operators, as you may know, it's not necessarily so that the ship owner actually also operating the ship. So the investor for the ship may be someone else who's actually buying the fuel. And in between, we have the port system. We have looked into how is this value chain adapted to actually accommodate for what you called cold ironing or shore power, and also supply of alternative energy supply to the ships. And we're talking then about electricity as a base case. As we found in the Norwegian study, shore power, while berthed in port, is possibly the lowest threshold for in many cases. It depends, of course, on what kind of ship, for how long does it stay in the harbor, and not least, how much can you actually utilize the assets you build in the port. As in any other industry, it's the utilization time of the full asset, which is the key to the profitability and the commercial activity. So we looked into different chains here, and we very fast coming to one important issue, and that is the case of integration across at least 3 to 4 players: the DSO, the grid owner, the ship owner and operators, the port, and the players actually providing the shore power or the charging system in the port. We've now several examples of ports around the world where one have invested in shore power or charging systems, but unfortunately finding there are no customers. That means the integration in decision processes is basically one of the most important issues for looking at. There are also other issues in terms of getting a system in place linked to standardization, linked to who's actually doing what, and not least, how can you utilize the same infrastructure for creating additional income streams. Electricity is quite simple, but the utilization time in harbors, ports, which we studied in the Norwegian analysis, we typically found the full capacity of installations we use maybe 700-800 hours a year. That is far too little to be in a competitive position unless you have say a high turnover of ships and repeat calls. That also points us in the direction how can we create some additional income streams. And as ports are not only a logistics hub for ships but also for rail and road transport, electricity supply to road transport quickly is coming up as one alternative. The second one is electrification of the port itself, forklifts, cranes, etc. And there's also supplying electricity, like one of the ports we look into in Norway, where the local bus company will have their main parking lot just next to the port, also using same transformer capacity for charging buses. This is important when looking into the total value chain, how you can actually create a combination of players. And that also is the really big challenge of this kind of investments, is it involves a lot of different players to get a coordinated decision process in place. That is also one of the main points. Are you back in online again, Paola?
Yes. Yes.
Excellent.
Thanks.
Will you take it?
Thanks. I can take over. Yes, thanks. So, as the coordination is the big issues, meaning that there is a significant investment risk in the decarbonization pathway. And one of the key aspects that goes on top of the coordination is also the uncertainty, not only commercial uncertainty given the utilization of the infrastructure, as Kjetil was mentioning, but there is also a technologically uncertainty. So assuming the case that we strongly invest today to electrify the port, so we will have to coordinate different actors and we will have to invest significantly in grid capacity because peak demand has to be managed. What happens if storage for propulsion would take place? This would further increase the needs for grid capacity. But if the scenario will change in the midterm and hydrogen, that as we mentioned before could be one of the leading technology for decarbonization will take place, this means that in the mid to long term, the infrastructure, the grid investments enlargement would not need any more needed, means that there would be a sunk cost for the system. So it's clear that coordination, technological choices and business model selection is complex because it has to happen simultaneously involving several different actors. Given this complexity, we have identified a number of measures that we believe can contribute or will contribute to a more efficient and comprehensive decarbonization of shipping. So if we move to the next slide, you can see that if we have a long-term view on what could be the pathway towards the decarbonization of the maritime sector, and we have as long-term a dominated hydrogen for decarbonize the sector, there are some measures that needs to be taken to help the system to evolve and mainly to sustain the coordination among different actors. So going back to the same picture that we show at the beginning, so policy, market and technology, we can see that a first movement has to be taken now at policy and market level. Policy should be for sure create a positive framework for cooperation among different actors that goes from traditional regulated, let's think to the DSO and network operators, to new potential investors, and create the right condition means probably also to provide some sort of financing support that could be capex for the harbor, but can even be a support for the investments retrofit at ships level. If there would be a policy support, there would be a following market development, so cooperation will take place between larger players. The cooperation mean also think about adaptation of business models. And when we talk about adaptation of new business model, we can think, for example, having an active role in facilitating the fuel conversion of ships, facilitate or put in place scheme for the retrofit of the ships, or generally also think to a role as energy service provider. If we move from this, that should be, according to us, the first step to be taken to boost the evolvement of value chain, and we move towards 2030, we can see that a second step of actions are needed. Again, some could be at the policy level. So some ad hoc incentives could be again needed for the development of some new technologies, and we have in mind hydrogen. But a key aspect would be the grid tariff. And according to our experience, we have seen a very different situation on relative competitiveness of power compared to other source and conventional source like marine gas oil, meaning that having a framework a good framework for tariff regime and a clear understanding of the impact for the system would be key for the development of the sector. Obviously, this could be only viable in a context where there would be a development from the technological point of view. And a couple of key aspects would be for sure the development of pilots for new technology, because as we said, they are still a completely different maturity between battery, hydrogen, and other sources. But also we would need a sort of standardization, because so far the standardization is still low, and would be a key factor if we want to develop significantly the shore power connection. Given this medium-term measure, we can then imagine how would be the path towards 2050. So once these ingredients that would be, from a policy point of view, support a market that would be able not only to cooperate but to develop also new business model, then we could imagine that we would be towards the path versus decarbonization. So where new technologies, the most efficient one, could take place, and we could achieve in the long term a complete decarbonization of the sector. So I think this was the overall picture of what could happen. So if we move to the wrap up, to leave a bit of space to your question, I think I can leave the word to Kjetil that can present you the remaining part.
Right. As I think is quite clear from the presentation so far, the complexity of doing projects and business development for decarbonization of ports and ships is possibly well outside of many of the other investment projects we see happening. Starting out from a, say, standard project cycles, we think the need for integration, the need for careful consideration at an early stage are possibly stronger in this kind of business development than many others. That involves 4 different areas: the market potential, strategy, business models, and policy incentives, which are typically early phase project activities. We're pointing to the importance that in order to do the right investment decisions, we need to have a careful analysis of the actual ship traffic, the potential, the surroundings around each port, what is available of infrastructure, and not least what have a focus on the stakeholder and value chain part of the business. We need to have an integration. This is one of the main points we made for the Norwegian authorities in our study when they were going to design the new investment schemes, investment incentive schemes, was that they should actually have 2 requirements. They would support consortia rather than single players, and they will always demand documentation of the market potential before providing investment support to a specific location. This is possibly one of the most important issues in early stage development, is look into what is the actual potential and who do you play with. The other main takeaway is the technological uncertainty. We know a lot about electricity. We do not think that batteries at any time will be able to cover much of propulsion need for longer distances, very much like we see on heavy transportation, road transport on shore. That means when looking into investments in electricity and start to look into charging for battery electric propulsion, we need to carefully consider what is the technology risk of hydrogen or other fuels becoming the dominating technology within a decade or 2. So flexibility, scalability, and solutions we go for, the risks of stranded investments needs to be carefully considered as well. The third one is that a port area today is basically a logistics hub. You move containers or the goods around. When introducing new fuels or electrical installations into the port area, we also have some new technical choices and new safety and security issues to take care of. The engineering itself is a question about, say, technology choice and standard choice, but there are quite a few new issues in physical security. Hydrogen is highly flammable. Ammonia is also flammable and poisonous. Electricity, installation of the magnitude we're talking about, commands a different security and safety regime than what is normally in place in a port. The fourth takeaway is the project design and project management. It needs to take into account the complex stakeholder environments and then a much more advanced project design than what we see in a, say, more limited investment project. That was all from our presentation. Matt, should we open up for some questions?
Thanks very much, Kjetil and Paola. Yeah, we've got a bunch of questions here, so let me just dive straight in if I can. The first one, and some of these were ones that came up in the registration. What will be the role of hydrogen in the decarbonisation of the port and ships? Can LNG play a role in the long term? How feasible do you believe that hydrogen fuel ships are in the mid to long term? Who wants to take that?
Yeah, I can take that. It's really three questions in one. And given our current knowledge of alternative fuels and our ability to produce them, some kind of hydrogen or power-to-X based fuel based on renewable energy and or CCS is a likely long-term solution. It's difficult to see, even with the most optimistic forecast on battery technology. We're now talking about maybe, say, a quarter to 1/3 of a kilowatt hour per kilo of battery. That is a small fraction of the weight you need to carry with hydrogen-based fuels. So I think we can actually say that if we are to be able to decarbonize shipping, it needs to be based to a great extent on hydrogen-based solutions in the long term, while there's a lot of technology development, not in the hydrogen itself, but in using it on board a ship in a sufficiently small and light fuel cell, or in an efficient enough internal combustion engine that could use like ammonia directly. That is going to take a few years before it's in place, and it will also take more years before you actually have that kind of propulsion systems in place in ships. Now, that being said, hulls, the actual ship, the hull of the ship has a much longer lifetime than the engine. So within a couple of decades, it's realistic that you can have a fairly substantial change in machinery on board ships. Then to LNG. LNG is, unless you produce it from biogas, it's still a fossil fuel. It's no long-term solution. It's better than MGO because it's a more efficient fuel on board, but it still emits CO2, so it's no long-term solution.
Okay, thank you very much. The next question here is, what is the panel's view on the length of time decarbonisation will take to fully initiate and widely be embraced?
Right. I think there are two main drivers, and given that at the starting point, CO2 is a commodity which we can't use for anything, we just want to get rid of it. It's no marketable or sellable product. That means the combination of policy and technology development will be very important to make the market work and make it, say, commercially more attractive to be decarbonized and continue using fossil fuels. We need some kind of regulatory push. That is, of course, much easier on a country level and an EU level for, say, the inland emissions than it is with national shipping. And that is one of the main challenges here. This is a lengthy process, and it will not happen overnight. As I said, also the time horizon for actually doing retrofit or new builds is also going to take some time. But within a couple of decades, like say by 2040 or so, is it realistic to have a fairly high degree of change in place. The Norwegian authorities' ambition of having a 50% reduction of CO2 from the inland shipping by 2030, we found is in reality quite unrealistic unless you in the meantime convert to biofuels. Thanks.
Okay, another question for you here. So do you have abatement cost curves for the sectors? And what sort of price triggers investment?
Abatement cost is, for the actual measures, is quite high. As we've shown previously, we can realize maybe up to 10% or so reduction, given the Nordic power prices and Nordic system for grid tariffs. We can maybe have a 10% reduction in CO2 emissions from inland and say sailings in Norwegian waters. That, of course, is far away from any, say, ambitious target for CO2 emissions. So the abatement cost in itself is quite high at this time. That is also coming back to the combination of policy incentives and technology development. We need to get technology costs down and efficiency up before this becomes attractive in an area near the current CO2 costs in the EU system.
Lovely, thank you. There's a question coming during the webinar, and I guess the answer, given what you've said so far, maybe you can just confirm, and that's around the impact of the current pandemic on what we're saying. My guess is that because you're talking about some of these things being sort of long-term developments on decarbonisation, that there shouldn't be too much of an impact, but maybe you could just clarify.
This is a question open to speculation and thinking about response. I mean, the positive thing about what we're seeing now worldwide on the pandemic is that the ability to react quickly is by far outside of anything we've seen before. Look at the lengthy process starting out in 1997 with the Kyoto Protocol and the CO2 discussion going on and on and on for decades, and things take time. Now, in a matter of weeks, the whole world had changed its whole modus operandi, admittedly in a way where you can actually do much of the work we've done on, say, a low investment cost like home offices, admittedly also with a substantial economic loss in terms of furloughs and redundancies. But it's likely to, say, put our, say, international ability to react in a different perspective. The other fundamental question is what will happen to transportation volumes? We see the actual road transportation across Europe has declined a lot over the last few weeks because actually we transport less, we commute less, we drive less. What will happen in the shipping industry? I haven't seen any statistics on this yet, but it's an open question. Will international trade and trade flows and trade volumes actually be reduced post-corona? Open to speculation. Yes, that would impact at least the emissions, same as it's done in many industrial sectors. But it's very difficult to say whether that would happen or not. You may argue that the pandemic is more driving towards more international cooperation than less.
Very good, thank you for that. And then one final question, because I see we are at time. I'll just ask one more question. What are the most important policy advice you would give to governments in order to get maritime decarbonisation going? What's your suggestion there?
I think that's a very clear message you also gave to Norwegian authorities. Design the incentives so that you force the stakeholders to cooperate. Do not accept single applications without having a full cooperation across the relevant value chain, going from source of energy down to the ship.
Great. Well, thanks everyone for joining our webinar. We have another one next week, which I think is going to be around the impact of coronavirus on forward curves and the outlook for especially for power prices. And within that, we'll be showing some results from one of our simulation tools that we use and sell, that is more focused on the short term and looks at really providing a fundamental approach to understanding what's behind a forward curve in terms of granularity and sensitivity. So that's coming up. If you know anyone that's interested in that, of course, these webinars are open to all. So please join us again. And I'd like to just thank Kjetil, Paola, and Johnny and Bev, who are helping us do all these webinars as well. Thank you very much, and see you next week. Cheers.